So, therefore, the right eigenvector for further clarification, actually this is your phi 1 1, this is phi 1 2 and this is phi 1 3. So, if you look into this phi 1 and phi 2 2, they are basically 1 2 rather, they are basically complex conjugate, because two eigenvalues are there. So, it is complex conjugate pair and one real eigenvalues. This the third your what you call that your third column, it is all are real. Similarly, this is your phi 2 1, this is your phi 2 2 and this is your phi 2 3, and this one is phi 3 1, this is phi 3 2 and this is phi 3 3, right. So, here also these two are complex conjugate, these two are complex conjugate, right. Now, if we for to get the left eigenvector, psi will be is equal to phi inverse, that we have seen, because your what you call that your phi into psi is equal to identity matrix, right. So, psi is equal to phi inverse. So, if you invert it, just let me tell you, if you invert it, that you will get that your psi phi is equal to I, right. Therefore, your psi is equal to your what you call that your phi inverse, right. So, in that case what you will get that if you take inversion, you will get this one. In this case also, this is your psi 1 1 and psi 1 2 psi 1 3, right. This is psi 2 1 psi 2 2 psi 2 3, you know it, but still I am writing psi 3 1 psi 3 2 psi 3 3, right. So, if you look into this column wise, these two eigenvalues are complex conjugate pair. Similarly, these two also complex conjugate pair, these two also, and third your row is basically real, because one eigenvalue is real. But only one thing I would like to tell, that suppose some questions are given in exam or assignment, we understand that 3 into 3 matrix inversion, particularly the complex one, is a time consuming process and difficult also, it consumes lot of time. So, in that case sufficient data will be provided, right, such that you by like phi psi all will be provided, such that you can easily compute the rest of the thing, right. So, now participation matrix, if you try to find out that P, right, it is directly computed that P actually is equal to this one. Basically, if you multiply like this, it will be basically phi 1 1 psi 1 1 this term, right. This will be phi 1 2, then just see whether I am not missing any term, that psi 2 1. If it is phi 1 3, it is psi 3 1, right. Similarly, this one, if it is phi 2 1, then it will be psi 1 2, right, and if it is your phi 2 2, then it will be psi 2 2, if it is phi 2 3, it will be psi 3 2, right. Just you have to multiply, all the elements are there for left and right eigenvector, and if it is phi 3 1, then it will be psi 1 3. This product of this, it is coming like this, if it is phi 3 2, then it is psi 2 3, and if it is phi 3 3, then it is psi 3 3. So, all these phi and psi elements are there in the right and left eigenvectors, and if you multiply, it will be like this, right. If you look into this, this first one is for delta omega r, then delta delta, and then delta psi f d, right. So, everywhere magnitude is 0.501, 501, everything here also, but this one 0.017, 017, this is 1.002, and here it is 0.001, 0.001. So, what does it mean, right. So, because three variables are there, delta omega r, delta psi and delta delta and delta psi f d, because it is 3 into 3 we have taken, right. So, this is for lambda 1, this is for lambda 2, and this is for lambda 3, right. So, based on that, this participation factor, your participation factor is computed. So, I have marked it, this is for lambda 1, lambda 2 and lambda 3. From the participation matrix, it is seen that delta omega r and delta delta have a high participation in the oscillatory mode corresponding to lambda 1, lambda 2. I mean, this is delta omega, this is delta delta. So, here also 0.501, here also 0.501, here also 0.501, here also 0.501, right. Therefore, the your delta omega and delta delta have a high participation in the oscillatory mode corresponding to eigenvalues lambda 1 and lambda 2. the field flux linkage has a high participation in the non oscillatory mode represented by the eigenvalues lambda 3. If you see the lambda 3 here, it is 1.002, it is high participation, whereas in that participation of delta omega r and delta delta is 0.017, very negligible, right. Similarly, for psi f d here in this two mode 0.001, almost negligible, right. So, the steady state synchronizing torque coefficient due to delta psi f d, this we know, this from the block diagram you pick up, right. So, this we have seen earlier, the steady state synchronizing torque coefficient due to delta psi f d is minus k 2 k 3 k 4, I mean k 2 k 3 k 4 minus symbol, that is we are taking from that block diagram, that is minus k 2 k 3 k 4, all the data were given initially, just multiply, it will be minus k 2 k 3 k 4 will be minus 0.3963, that means k 2 k 3 k 4 is equal to, this is minus k 2 k 3 k 4 we have taken. So, minus 0.3963, that is k 2 k 3 k 4 is equal to 0.3963, right. The total steady state synchronizing torque coefficient, so it is k 1 your minus k 2 k 3 k 4, right. So, it is k 1 minus k 2 k 3 k 4, k 1 is given 0.7643 was given in the data, and k 2 k 3 k 4 here k 2 k 3 k 4, right, this value you substitute that k 1 minus k 2 k 3 k 4. So, whatever it comes, that is your k s synchronizing torque coefficient, right. Therefore, k s is equal to 0.3679 per unit torque per radian, right. Now, from the block diagram of figure 31, right, figure 31, just check figure 31 or figure 30, please check this one, both block diagram are same, you can take 30 also, just check, right. Only that PSS term may be there, but this figure 30 or figure 31, probably figure 30, just check, right. So, if it is figure 31 also, just see similar diagram, only one PSS term may be there, right. So, delta T s upon delta delta s due to delta psi f d, we know this, minus k 2 k 3 k 4 upon 1 plus S T 3, right, or delta T upon delta delta, instead of due to delta psi f d, just due to delta psi f d, we are writing minus k 2 k 3 k 4, numerator and denominator you multiply by 1 minus S T 3. So, it will become this one multiplied by 1 minus S T 3 upon 1 minus S square T 3 square, right. Therefore, delta T due to delta psi f d, that means multiply both side by delta delta. Therefore, delta T due to delta psi f d will be minus k 2 k 3 k 4 upon 1 minus S square T 3 square delta delta plus k 2 k 3 k 4 T 3 upon 1 minus S square T 3 square S delta delta. These two terms we are separating, right. So, one is delta delta, another is S delta delta. Oh, this is from figure 31, that PSS term is there, that your that thing, right. So, it is correct one, figure 31. So, go back to figure 31, I am not going, even figure 30 also you will get the same thing, right. It is just development step by step. Therefore, delta delta is omega 0 upon S delta omega. Therefore, S delta delta can be written as omega 0 delta omega r, right. Here it is S delta delta. So, replace this S delta delta by this omega 0 delta omega r, right. Therefore, delta T due to delta psi f d is minus k 2 k 3 k 4 upon 1 minus S square T 3 square delta delta plus k 2 k 3 k 4 T 3 upon 1 minus S square T 3 square, then into delta omega r into omega 0, right. So, this is delta T in your what you call in terms of delta delta and delta omega due to delta psi f d, right. Now, this is simple thing, just go back to your figure 31, right. Again and again I am not going, just when you will listen to this, just keep figure 31 in front of you, right. Therefore, this can be written as, this thing can be written as that delta T due to delta psi f d k s delta psi f d, that means k s due to delta psi f d into delta delta plus k d, the damping part, delta psi f d, it is synchronizing torque coefficient, it is damping torque coefficient, k d into delta, this is due to delta psi f d into delta omega r into omega 0, omega 0 is your 2 pi f 0, right. From the eigenvalues, the complex frequency of rotor oscillation we have seen, it is minus 0.11 plus j 6.41, right, but this real part is very small compared to the imaginary part. So, for our approximate analysis more or less it is true, we will ignore the real part, right. Since the real component is much smaller than the imaginary component, we can compute Ks and Kd at the oscillation frequency by setting S is equal to J 6.41 without loss of much accuracy, because this one we will ignore, right, because it is very small. So, only we will take that we will substitute in this equation, S is equal to your J 6.41, here we will substitute, right. That means K's delta psi f d has been defined as 1, that is minus K2 K3 K4 upon 1 minus S square T3 square. This is actually K's due to delta psi f d into delta delta. So, this is my K's delta psi f d is equal to this term, right. I mean this one actually K's delta psi f d, right, and this one, right, whatever it is, this one is given, right, this term. Later we will see it is K d your delta psi f d, right, omega 0 term is also there, that is constant. So, if we do so, right, then put K2, K3, K4 all we have got it, it is 0.3963 and divided by 1 minus J 6.41 and T3 value was given in the data 2.365 whole square. If you simplify, Ks due to delta psi f d is becoming minus 0.00172 per unit torque per radian. It is a dimensionless quantity, right. Similarly, Kd delta psi f d is Kt, K2, K3, K4, T3 into omega 0 upon 1 minus S square T3 square, right. So, K2, K3, K4 we have computed before 0.3963 into 2.365, that is T3 into omega 0, it is 60 Hz, so 377, right. 2 pi f 0 we have taken f 0 is equal to 60 Hz divided by 1 minus J 6.41 into 2.365 square. If you simplify, it is coming actually Kd delta psi f d is 1.53 per unit torque per unit speed change, that is basically a dimensionless quantity, right. Therefore, the effect of field flux variation, that is the armature reaction, right, is thus to reduce the synchronizing torque slightly and to add a damping torque component, because this is actually Ks is minus 0.00172, negative means that it is effectively slightly it will reduce, right, because it will be K1 minus Ks, right. Therefore, the net synchronizing torque component in general we write K1 plus Ks delta psi f d is equal to K1 is given 0.7643 and Ks due to delta psi f d we got minus 0.00172. So, more or less unchanged, right. So, it is 0.7626, right. Similarly, the only source of damping is due to the field flux variation, hence the net damping torque is Kd, because other Kd in the data Kd was given 0, there was no Kd. So, it will be simply as Kd is equal to Kd delta psi f d, that is 1.53. It is a dimensionless quantity, but we are writing per unit torque by per unit speed change, right. Now, we know the undamped natural frequency is this expression we have made it earlier, omega n is equal to root over Ks omega 0 upon 2h. So, Ks we got 0.7626, omega 0 2 pi f 0 is 60 Hz, so 377 and 2 into h in the data given 3.5. So, omega n is actually 6.41 radian per second, right. Now, here also if you look into this, that here also if you look into this, that it is 6.41, right. So, I mean just it is your what we call just telling that according to our data it is coming like this, but nothing to relate with that, right. And similarly, your xi, that is your damping ratio, that also we have derived before, that is half into Kd upon root over 2h omega 0 Ks. If you substitute that your h is your what you call 2h, right, omega 0 Ks, Ks is actually 0.7626, then 2h 2 into 3.5 into omega 0 2 pi f 0 377. So, xi is 0.0171, right, this is the answer. So, the above values of omega and xi agree with this computed from the eigen values, right. So, if you see the eigen values and see this one, you will find that omega n also we got 6.41, right, and here also we got this thing. So, it agrees with that, right. That means that approximation is okay, and just have a look, right. So, this is the your what you call that your another example, right. So, now question is that participation factor we have studied already, and we have seen that P is equal to your in general phi into psi in matrix form, right. That also I told you how to take it. Now, see little bit more. So, participation factor analysis again aids in the identification of how each dynamic variable affects a given mode of eigenvalue, specifically given a linear system, say x dot is equal to x, right. Actually, this is I have written small, then you take small x, right. This equation we have made it 36a, right. Just we are trying to put it in another way, right. So, a participation factor is a sensitivity measure of an eigenvalue to a diagonal entry of the system A matrix. This we have seen earlier, but why I have taken this again, just we will see. So, this is also we have defined that p k I is equal to delta lambda I upon delta a k k. This is equation say 37, right. While lambda I is the ith system eigenvalue, a k k is a diagonal in the system A matrix, and p k I is the participation factor relating the kth state variable to the ith eigenvalue, right. So, this is your what you call we have seen before, right. Now, the participation factor may also be defined by p k I is equal to w k I v k I upon w I v I. Actually, v k I is the your what you call w k I and v k I are the kth entries in the left and your right eigenvector. Actually, v k I is nothing but your phi k I previously we have taken the right eigenvector, and w k I is nothing but psi k I, that is your left eigenvector, meaning is same, right. As I have taken different example, that is why this terminology I have changed it, right. So, it is w k I v k I upon w I transpose v I, this is equation 30. So, basically your this is actually v k I is not v actually nothing but phi, that is right eigenvector, and w is nothing but psi, that is your left eigenvector, right. So, where w k I and v k I are the kth just hold on, are the kth entries, right, in the left and right eigenvector associated with ith eigenvalue, right. The right eigenvector v I and the left eigenvector w I. I have written here phi I actually v I and psi I is equal to w I, hence there is no confusion, right. Associated with the ith eigenvalue lambda I, satisfying this we have seen before. There it was a phi I is equal to lambda I phi I, but I am putting here a v I is equal to lambda I v I, and here your there it will be your psi I transpose A is equal to psi I transpose lambda I, here is w I transpose A into is equal to w I transpose lambda I. This is equation 40, right. Now, it is not obvious that the definition given in equation 37 and 38 are equivalent, right. So, let us establish the equivalence as follows, right. So, for example, consider the system, this we have seen earlier, that your a minus lambda into I into v I is equal to 0 to find out your right eigenvector, this we have seen before also, right. And another one left eigenvector w I transpose, we are making a minus lambda I is equal to 0, this is 41, this is 42, right. Now, where v I and w I need not be normalized eigenvalues. So, v I and w I it need not be normalized eigenvalues, right, but this we have seen before. It is our goal to your what you call to examine the sensitivity of the eigenvalue to a diagonal element, right, the diagonal element of the A matrix. So, from equation 36a, that is x dot is equal to your A x, right, I believe equation 36a, that is x dot is equal to A x, right, right. So, from equation 36a, that assuming that the eigenvalues and eigenvectors vary continuously with respect to the elements of the A matrix, right, say we assume this one, right. We write the perturbation equation as, that means this equation can be written as this equation 39, it can be written as, right, equation 39 it can be written as A plus delta A into V I plus delta V I is equal to lambda I plus delta lambda I into V I plus delta V I, right, if it is like this, like your small perturbation thing, right. So, this expansion gives, if you multiply, it will be A V I plus in bracket delta A into V I plus A into delta V I plus delta A into delta V I is equal to lambda I V I plus bracket delta lambda I V I plus lambda I delta V I plus delta lambda I delta V I, but delta A into delta V I, this term, this quadratic type of terms we will neglect, this term and these two terms we will neglect, we assume that its contribution is negligible, and this is equation 44, these two terms we will neglect, right. So, if we do so, neglecting the terms that delta A delta V I and delta lambda I delta V I, and using equation 39 we obtain, right. That means, this is your, just you have to go back to equation 39, right. So, basically you neglect these two terms and from equation 44 and 39 you will get A minus lambda I into I delta V I plus delta A V I is equal to delta lambda I V I, right. But this term A minus lambda I into delta V I is 0, that we have seen, right. This A minus lambda into delta V I plus delta V I is equal to delta lambda V I. Now, multiply, this is not 0, we will come to that, sorry. Now, multiplying equation 45 by the left eigenvector. So, please multiply this equation by your left eigenvector. So, say W I transpose, right. So, A minus lambda I into delta V I plus W I transpose delta A into V I is equal to W I transpose delta lambda I V I, right. The first term in the left hand side of equation 46 is identically 0 in view of equation 42. So, come to equation 42, right. If you see equation 42, that A minus lambda I your into I V I, that was delta, but multiplying both sides W I transpose into A minus lambda I is equal to 0, right. So, if you come to this equation 45, right, here if you come to this 46, so W I transpose A minus lambda I, this term effectively is 0. So, this term is 0. So, if it is so, then the first term, so if it is so, then this equation can be written as W I transpose delta A V I is equal to W I transpose delta lambda I V I, right. So, that means your this equation, now from this equation we will get this expression same as before. Now, the sensitivities of lambda I with respect to diagonal entities of A are related to the participation factor as follows, right. Only diagonal elements, right, A k k, A j j, like this, right. So, in that case assume that only the kth diagonal entry of A is perturbed, right, only kth element. So, that means delta A, all other elements remain fixed. So, its perturbation is 0, only kth element, that is A k k, is perturbed. So, it is delta A k k, right. This is equation 48. So, previously whatever we have done, so now concept will be clear, right. So, then in equation 47 the left hand side can be simplified as it is W I transpose delta A V I is equal to W k I A k k V k I is equal to W I transpose delta lambda I V I. That means, delta A, this delta A actually this delta only kth element, right, only diagonal element, that kth row and kth column, the diagonal has to be perturbed. So, delta A is equal to delta A k k. So, this is in general we can write then, because now it is only single element delta A k k. So, we can write W k I A delta A k k V k I, right, is equal to your W I transpose delta lambda I V I, the right hand side, right. Therefore, solving for the sensitivity, it gives the your participation factor, right, as therefore, delta lambda I upon delta A k k is equal to W k I V k I upon W I transpose V I is equal to P k I. This is equation 50. So, we see another form of participation factor. Now, equation 50 that shows that equation 37 and 38 are equivalent, right. Now, an eigenvector may be scaled by any value resulting in a new vector which is also an eigenvector, right. So, we can use this property to choose a scaling that simplifies the use of participation factor, right. For instance, choosing the your what you call eigenvector such that W I transpose V I is equal to say 1 simplifies the definition of the participation factor that we have seen also, that k is equal to 1 to n is W k I V k I is equal to W I transpose V I. Similarly, this thing we have seen also, that k is equal to 1 to n, this is psi k I phi k I is equal to, it can be written as psi I transpose then phi I, right. So, it follows from equation 50, that means from this equation, right. It follows from equation 50 that the sum of all the participation factor associated with a given eigenvalue is equal to unity, that is 1. That means k is equal to 1 to n, p k I is equal to 1. This is 51, that means it is normalized, right. This property is useful since all the participation factor lie on a scale from 0 to 1, right. So, previously when you started participation factor, everything has been mentioned, but once again I thought I should take it little bit in a different way such that that idea will be clear, right. So, now to handle participation factors corresponding to complex eigenvalues, we introduce some modification as follows, right, because you have earlier we have seen participation factor and complex values, right. Now, the this is another form, the eigenvectors corresponding to a complex eigenvalue will have complex element, right. Hence, p k I is defined as, p k I can be taken as mod of v k I, that is absolute value, then absolute of w k I sigma k is equal to 1 to n absolute of v k I into absolute of w k I. This is equation 52. When I will take couple of example, you will find things have been very transparent, right. Only my suggestion to all of you, just try to understand a little bit, try yourself derivation, and little bit you have to keep it in your memory from the point of view of your examination, you have to keep it this in mind, right. So, a further normalization can be done by making the largest of the participation factor equal to unity, right. So, example, so compute the participation factor of the 2 into 2 matrix x dot is equal to x, where A is equal to 1 4 3 2, right. So, this is your what you call that your a matrix is given, right. Now, the eigenvalues of this matrix you can easily find it out. So, eigenvalues are lambda 1 is equal to 5 and lambda 2 is equal to minus 2, right. So, in this case your eigenvalues are real. Now, you following the same procedure you find out the right eigenvectors, right. It is V 1 the first column of the matrix 1 1 and V 2 4 minus 3. That means, your basically your phi is equal to nothing but V, the right eigenvector. So, first column that is 1 1 and that is your 4 minus 3. This is actually my right eigenvector, right. So, this way we write like this, V 1 means the first column, V 2 means the second column, right. So, if you find out right eigenvector following the same procedure, you will get like this, right. So, the left eigenvectors similarly you can compute. So, it is given W 1 your transpose, that is 3 4 and W 2 transpose 1 minus 1. That means, your basically psi is equal to W, the left eigenvector. This can be written as actually 3 4 and it is 1 minus 1, this way it can be written, right. So, your basically it is your what you call that your psi transpose W transpose, this way we can write, right. So, that is why it is written, that was column wise, this is row wise, right. So, now to verify that you will see that W, just hold on, W 2 transpose V 1 is equal to W 1 transpose is equal to 0. For example, W 2 your transpose, that means this one actually 1 minus 1, right, and then your V 1 that is 1 1. If you multiply 1 into 1 minus 1 into 1, it is basically 0, right. So, it is 0. Similarly, if you make W 1 transpose, right, this one 3 4 into your 4 minus 3, that is 3 4, I am making it here for you 4 minus 3. So, 12 minus 12. So, it is 0. So, W 2 transpose V 1, W 1 transpose V 2 is equal to 0. Please you do it yourself. I have given the final thing, you find out right eigenvector and left eigenvector. Of course, you know this, right. So, now to verify this, right, also W1 transpose V1 is equal to 7 is equal to W2 transpose V2, you can do it, you will get 7, right. Now, letting I is equal to 1 and k is equal to 1 2, your successively we obtain the participation of the state variables x1 and x2 in the mode lambda 1 5. You take that your what you call that expression is there here, no expression is there, your what you call pki expression is there, right. So, in that case your this thing your what you call you take 1 by 1, right, 1 by 1, this is your what you call that total is per unit is 1 and here it is right. So, if you look into this expression that you put your in this case I is equal to 1 and k is equal to 1 2, that means this equation you put your I is equal to 1 and k is equal to 1 to 2, that means n is equal to 2, right, and you do this, you will find if you do so and simplify, you do this, you simplify, you will get P11 will become W11 V1 upon W1 transpose V1, because another term will become 0. So, it will be 3 into 1 upon 7 3 by 7 and P21 W21 V21 upon W2 transpose V2, it is 4 into 1 upon 7, right. So, basically it will be 4 by 7, 3 by 7, 4 by 7, if you add it, it will be unity, P11 plus P21 will become unity, right. Similarly, for I is equal to 2 and k is equal to 1 2, you will get P12 W12 V12 upon W2 transpose V2, that will get 4 by 7 and P22 will get W22 V22 upon W2 transpose V2, that is 3 by 7, right. So, participation matrix P11 P12 P21 P22, it is 3 by 7 4 by 7 4 by 7 3 by 7, there we did phi into psi, phi 11 psi 11, phi 12 psi 21, phi 21 psi 12 and phi 22 psi 22, here directly you are getting it, right, using that matrix, because everything has been taken care of, right. So, please go through this, right. Normalizing the largest participation factor as equal to 1 in each column, that means largest is your 4 by 7, divide this all the element by 4 by 7. If you do so, it will be P normalized 0.750 1.75, right. So, thank you very much, we will be back again.